Section 2.3 continues. We're going to continue here with the remainder and factor theorems. This is a follow-up of the synthetic and long division problems that we just did. This theorem, the remainder and factor theorems, think of them as basically saying the same thing. It gives us a way that we can evaluate a polynomial function using synthetic division. Basically, if we divide by x minus a number or x plus a number, which is the only kind of problems that we can do synthetic division with. If it has a number in front of the 2, like a 2x minus something, then we can't do synthetic division with it in that form. So we're only talking here about problems with we're dividing by x minus or x plus a number. Basically, the remainder that we get is the same as the function value at whatever number we are subtracting. It'll make more sense in the context of an example. So let's consider this example here. We have a function f of x equals 7x squared plus 2x minus 1. One way to evaluate the function at x equals 3 is the way that we've always done it. We're just going to take 3 and we're going to plug it in for x in these places, and this is what that would look like. 7 times 3 squared plus 2 times 3 minus 1. When we evaluate that, we are going to get 9 times 7 is 63, plus 2 times 3 is 6, minus 1. Well, this equals 63 plus 6 is 69, minus 1 is 68. What the theorem up here allows us to do is to evaluate this another way, a different way we're going to get 68. And what that is we're going to do synthetic division with this number as if we were dividing by x minus 3. So this number goes inside the box, 3. You'll see that down here. Now the coefficients, 7, 2, negative 1, go here. We're going to do our synthetic division, and what we're going to see is the remainder that we get at the end here is going to be 68. It's just another way to evaluate the function. So 7 comes down, 3 times 7, and we add, we multiply, that's 69, minus 1, 68. So this here is another way of getting this number. Just another way. It's really doing the same thing. That's the remainder and factor theorem, basically. Before we go to the next slide, I should point out that if the result that you get, either by plugging in or by doing the synthetic division, if you get a 0 for a remainder, that tells you that x minus this number is a factor. All right, hopefully we got that from the first video. The last thing we'll talk about here is the rational zero test. This is a way to test for how many possible rational zeros we can have. Now, before we get into that, we have to remind you what a rational number is here. A rational number is a number that can be written as a fraction of two integers, or the quotient of two integers. Pi, the number pi, is an irrational number. You can't do this with pi. You cannot take it as one integer divided by another integer and get pi. That's impossible. A reminder about what pi is what we get when we take the circumference of any circle, which is the distance around a circle, and we divide that by its diameter. We get pi, no matter how big or how small the circle is. That's an irrational one. What we're looking for here, what this test does, is it'll find out how many rational zeros we can get in a function. So here's what it says. When a polynomial has integer coefficients, so these must be integers here, we can't have fractions, every rational zero will be of the form p divided by q, where p is a factor of the constant term. That's the last guy there. And q is going to be a factor of the lead coefficient. So it'll make more sense if we look at this example here. So consider this function, 3x cubed minus 7x squared plus 5x plus 2. Problem that you might encounter will say something like this. use the rational zero test to list all the possible rational zeros of the function. Well, the theorem above tells us that if there are rational zeros, they got to be in the form of p divided by q. P is going to be the factors of the constant term. Well, the constant term in this problem right here is 2. Let's highlight that here. Okay, here's our constant term. So what are the factors of 2? Positive or negative 1? Positive or negative 2? That's the only factors there are of 2. Now in the denominator, q, that's the factors of the lead coefficient, which here is this 3. Well, the factors of 3 are positive and negative 1 and positive or negative 3. So I'm going to make a fraction, every possible fraction I can make with these 4. The only 4 things I'm going to come up with is 1 over 1, which is 1, so positive or negative 1. 1 over 3, so that's going to be positive or negative 1/3. Now using the 2, 2 divided by 1 is 2, so we're going to have positive or negative 2. And the last one would be 2 over 3, so positive or negative 2/3. It doesn't guarantee us that these are zeros, but if there are rational zeros, it's got to be one of these 4 things. So here's another problem. You can pause it and see if you can list all possible rational zeros in this. Rational zeros must be of the form p divided by q, p being the factors of the constant term out here, which is negative 1. So factors of negative 1 are just going to be positive or negative 1, divided by q, which are the factors of the lead coefficient, which here is 7. Well, that's only positive or negative 7. So basically, what I've got here is I could have positive or negative 1/7. That's it. Well, since there's only 2 of those, this is easy for me to show you. So what I'll do, let's see if either one of those 2 things are zeros. I'm going to bring up the calculator here. What we'll do is we'll plug in 1/7 and negative 1/7 into that function. Minimize this, this, okay. First thing I'm going to do is I'm going to say, let's start with positive 1/7. So 1 divided by 7, I'm going to store that as the x. So STO down there, and then x. Hit enter. Now every time you use x, it's going to put 1/7 in there for us. So I'm just going to type in the function here. I have 7x to the 4th power minus 3x squared plus 2x minus 1. We hit enter. We do not get 0, so 1/7 is not a rational zero. So now I will try the negative 1/7. So I'll start with negative 1 divided by 7. Close the parentheses. I'll store that as the x. And now I'll bring up the command by hitting second enter a couple times. There's the function. Enter. I don't get 0 again. So neither one of these 2 are rational zeros. So my conclusion on this particular problem is going to be that we have no rational zeros. They must be irrational. Okay, so that's an example of the rational zero test. So I'm going to give you some problems to practice on this. I tried going a little bit easy here, giving you the minimum. Feel free to do more problems in a particular section if you need to. But this, again, we're looking for understanding here, so try these out. Giving you some odd problems so that you can have access to the solutions. I'm having you do 35 to 37 all, so there's an even one in there. We can do that in class if we want to check that one. and then 39, 41, 45, 47, and 49. I tried taking it easy, but these are things that you're going to be tested on. You do have to know how to do them, so you do need to practice. So I hope this helps. Watch it as many times as you need, and bring me your questions.